Hello ladies and gentlemen, my name is Simon Schmidt. I'm head of the Hygrothermics department at the Fraunhofer Institute for Building Physics IBP. For a good indoor climate and for the avoidance of hygrothermic problems such as mold growth, it must be ensured that there is a regular exchange of air in the room. We will deal with this in the first part of the video. In the second part, we will then look at the effects of thermal bridges on the energy efficiency of buildings. Let's start. How do we measure the air exchange rate in the room? The air exchange specified in the quantity N lower L. This quantity indicates how often the complete volume of an air in the room is exchanged within 1 hour. Here you can see typical values. For example, if we have a closed door, a maximum of half the air volume is exchanged through leaks in 1 hour. This means that it takes 2 hours, 120 minutes, for the entire air volume to completely exchange. With a half open window, on the other hand, the air volume is completely exchanged about 5 to 10 minutes in 1 hour. Or the other way around, it takes around 6 to 12 minutes of window ventilation to completely exchange the air in the room once. The values you see here were determined by numerous tests. As you can see, cross ventilation is most effective with an air exchange rate of 20 to 40. Here the air volume is exchanged within 3 minutes. Let's check that types of ventilation are possible in the building in INDORE. We can keep windows and doors completely closed and there is only a low air exchange through leaks and the air exchange rate below 0.5. We can tilt the windows to create a low air exchange rate. As you can see, the thickness of the arrows shows here is to give an impression about the air exchange rate. We can further increase the air exchange rate with half open or even fully open windows. And due to the arrangement of the apartment, it's also possible to ventilate crosswise very effectively and thus exchange the complete air volume in the apartment within a few minutes if necessary. So we have different options to a complete air change in 3 to 120 minutes. Now let's move on to the topic of the thermal bridges next. We already learned in the module 1.2 that thermal bridges are localized areas in the heat transferring envelope where an increased heat flow occurs compared to the normal wall construction. That happens mostly in corners of rooms or also on certain materials. Now to calculate the heat flux that is additionally caused by the thermal bridge, we use this formula. HTWB is the total heat flux including the thermal bridge effect. HT is the heat flux through the regular wall and QWB, the thermal bridge heat flux, needs to be identified first. Therefore, we can use the following equations. The thermal heat bridge flux consists of two different elements, the heat flux through the point thermal bridges and through the linear thermal bridges. Here you see how they are calculated. Point-shaped thermal bridges corresponding to approximately 2 to 5% of HT in sum. Linear thermal bridges correspond to approximately 25% of HT. Now let's take a closer look at two examples below. Using the Lighthouse project in INDORE as an example, there are two clear thermal bridges that should be investigated. On the one hand, the corner detail. Here, the steel beams creates a thermal bridge connection to the outside air with the inside air. Secondly, the girder connection in the middle of the outer wall of the apartment. Here, too, a thermal connection between the outside and the inside air is created. In the following, we will take a closer look at thermal bridges from the grinder connection. Here we see the thermal bridge just discussed. With the help of simulation programs, the temperature curves over the component cross-section can now be determined. The color indicates the magnitude of the heat flux, with purple being a low, meaning a good value. The more it goes toward the red, this color scale, the higher the unwanted heat flux is. You can see the clear influence of the thermal bridge in this construction. Let's take this as a reference case and see how we could improve this construction in detail. So let's take this heat flux as 100%. To improve the thermal bridge, insulation was installed inside the improved interior case. We see a significant improvement and a decrease in the heat flow above 90%. In the optimized version, additional insulation, also installed on the outside, is introduced. The decreasing influence of the thermal bridge can be clearly seen. The heat flux drops to 80%. With simple insulation methods, it is therefore possible to reduce the unwanted heat flow by 20% and thus significantly increase the energy efficiency of the overall structure. Let's conclude by summarizing the main findings from the unit. Any from the ventilation is possible in the apartment in the Lighthouse project INDORE, even the very efficient cross-ventilation. There are two different types of thermal bridges, point and linear. The calculation is quite feasible on the basis of existing equations. A closer look at optimization of thermal bridges can in many cases significantly increase the energy efficiency of a building, as unnecessary heat transitions can be avoided. Thank you for your attention and goodbye.